Hello everyone, welcome to the lecture series on Foundations of Deep Learning, Concepts and Applications. So far, in the last 2 weeks, you have learned the fundamentals of a neural network, including the concepts of single layer perceptron and multi-layer perceptron. You have explored activation functions, you have understood the role of optimizers and implemented multi-layer perceptron model through hands-on learning exercises. We have also discussed the various regularization techniques and saw their implementation. Now, from week 3 onwards, we will be moving into one of the most exciting and powerful areas of deep learning, convolutional neural network. Over the next 2 weeks, that is week 3 and week 4, the following topics will be covered in detail. In week 3, since we will be dealing with the images, initially we will be learning the fundamentals of image representation. Then we will go into the architecture of CNN, where we will learn in detail about the different layers in CNN, and then we will also see the regularization techniques that we will be using for CNN model. And towards the end of week 3, we will be seeing the implementation of CNN using Keras. Coming to week 4, once the fundamentals of architecture of CNN is made clear, we will be moving into the various variants of CNN, various architectures of CNN, where you will be learning the AlexNet, BGGNet, you will be learning the GoogleNet, ResNet, Inception, transfer learning. We will also be implementing all of these models without transfer learning, and we will also be implementing them with the transfer learning. And towards the end of week 4, you will also be learning the ensemble model, how to build an ensemble model. So, by the end of this segment, you will have a very strong foundation in CNN architecture, its working principle and practical implementation using Keras. So that we will be preparing you to the more advanced applications in CNN. So, with this, let us get started. For today's session, the following are the topics that we will be covering. We will first see the fundamentals of image representation, and then we will also learn how many number of channels are there for each of these image types. Why not use a fully connected neural network when we are working on images? What exactly is the problem? We will understand that, and towards the end of this session, we will learn in detail about the various data augmentation techniques and how do you store the data so that you can work with the CNN. So, since we are working since the topic is all about the CNN, there are so many images that we will be using. Therefore, all the images that are used in this presentation are sourced from publicly available academic and internet resources only, and these are used solely for educational purposes, so that we will have a better understanding of CNNs. The key references that are used for learning CNN are the following are the references. Deep learning authored by Ian Goodfellow, and we have a course by Stanford University, that is a course on deep learning for computer vision. Most of the concepts are taken even from this particular. And then we have a very good textbook, that is a deep learning with the Python. So, the following are the 3 different references that are used for this particular series. Yeah. So, when it comes to images, the following are the possible images that one can be working on. You can work on RGB images, that is color images, or you will be working on a grayscale image, or it can be on a binary image. The following, I am not talking about the formats. The formats can be JPEG, PNG, TIFF format. There are so many other formats. I am saying the possible different types that you may be working will be either RGB, grayscale, or the binary images. Okay, now before we go into the details, let us understand how does the system actually read an image. When you look into this particular image, and when we closely observe this image will have the collections of small boxes. If you look into, we have many such small boxes, and what exactly is each of these box called? We call it as a pixel. Therefore, each pixel, we have a pixel here, we have a pixel here, we have a pixel here. Each of these pixels in an image is represented by a numerical value. Now, these numerical values are called pixel values. So, how does the system read an image? A system will read an image as a grid of pixels. Now, when you look into an image is having a dimension. We have an x-axis and we have an y-axis. So, what exactly is this dimension? The dimension of an image are defined by number of pixels along its height and width. So, how many number of rows are there and how many number of columns are there? So, this is how we define the dimension of an image. If this is the case, what is an image? Image can be represented as for a grayscale, this is the representation. For a binary, this is a representation. For an RGB, this is the representation. If you look into each of this, it looks like a matrix. It is a matrix. Why it is a matrix? Because we have rows and we have the columns. So, it is a matrix. Matrix of what? Matrix of a pixel values. So, image can be represented as a matrix of a pixel value, where each of these values, if you look into each of these values actually denotes the intensity of the pixel. It denotes the intensity of a pixel. So, for a grayscale, what does it defines? It defines the brightness. When we talk about an RGB, each of these pixel actually defines the color intensity. So, with this image can be represented as a matrix of pixel values. Let us learn one of the most important concept, and this is very much useful when we are doing the hands-on. So, how many number of channels are there for each of these image type? So, when this is a colored image, what example we are seeing here is a colored image. Now, when you see this color image, this is actually a combination of R, G and B component. So, we will have for red, if red this is one image, green this is one image, blue this is one image. So, we have seen from the previous slide that image is represented as a matrix. So, for a red we will have a matrix, for green we will have a matrix, and then a blue we will have a matrix. So, how many such matrix are there? The number of channels will be 3. Why it is 3? Because we have 3 components that will define one pixel. So, if you take, there is a pixel value here, there is a pixel value here, there is a pixel value here. Each of these pixel is actually a combination of 3. So, how do we represent? A pixel here will be represented as a combination of 3 values, where the first will be the R component, the second will be the G component, and the third will be the blue component. So, let me clear this screen. If you look into, this is what has been explained. Each pixel is actually a combination of 3 values. What are those 3 values? We have an red component, green component, and then the blue component. Therefore, the number of channels that are used for an RGB will be the 3. The number of channels here are 3. We will have 3 channels. Okay. Now, how many number of channels are there when we are dealing with the grayscale? So, this is an example for a grayscale. Now, if you look into this image, this is left side is one example, this is one example, and this is an second example, just for an better understanding. If you look into an example 1 here, this is an example of 8, it is an handwritten 8, and if you look into here we have values 0, and if you see we have a value 255, and then we have all the values between 0 to 255. Now, how many number of channels are there for an grayscale? The number of channel here is 1. Why exactly there is 1? Now, if you look into this very carefully, we do not have different colors. We cannot say black and white are two different colors here. We have we can see this as white is equal to 255 minus the black intensity. So, if you take 255 when there is no black component, so it is just the value is 255. So, second example, if you take, it is 255 minus if you take some value, then you will have some other number which is not completely white, but it is closer to white. Similar way, in this place, whatever the value that we substitute, suppose we substitute 255 only. So, we get 0, which is completely black. So, we cannot say that there are two different colors. They are on a same single channel, they are at two extreme points. Therefore, the number of channels that we will be using for a grayscale is 1. This is the number of channel. So, for a grayscale we have one channel. So, likewise, when we are dealing with the third type of image, that is binary. So, this is an example for an binary. It is an image which is represented in a binary format. Since the number of colors here are only 2, which is either 0 or 1. Therefore, the number of channels that we will be using for an binary image is 1. So, with this let us quickly look into a summary, how many number of channels, because this is one of the important concept when we are doing an hands-on implementation. So, the 3 different types of images that one will be working will be either you will be working on color, you will be working with color images, or you will be dealing with the grayscale, or it can be an binary image. So, if it is an grayscale, if it is an RGB colored image, the number of channels, the value is 3, and if it is an grayscale, the number of channel is only 1, and the value will range anywhere between 0 to 255. So, 0 represents black, 255 represents white, and then in between we will have the different shades. So, we will say it is a grey. And then the third type will be a binary. So, number of channel here is only 1, and the value will be either 0 or 255, or we can write it as 0 or 1. So, this is all with respect to the number of channels. Now, let us get into the next important concept. In week 1 and 2, we have seen in detail about the multi-layer perceptron, that is artificial neural network multi-layer perceptron. So, multi-layer perceptron is used to solve a regression problem, it is used to solve a classification problem. So, the model was performing very well. So, why can't we use the same model when we are dealing with the images? So, what exactly is the problem? If you look into this image very carefully, this we call it as an input, and this is an output, and in between we have an hidden layer. This is all hidden layers. So, since we have multiple layers, we call it as an multi-layer perceptron, MLP, multi-layer perceptron. Now, what exactly is this input? Now, if you remember, we will have our data set. In the data set, we will have multiple features, and the last one is the class label. So let us not bother. How many ever number of features are there? So many number of neurons that you will put at an input layer when you are building an architecture. How many number of neurons, how many number of features? So many number of neurons at an input layer. Okay, so this is with respect to if you are taking an data set in the CSV format or a structured data. Now, what is that we are dealing with? We are not dealing with structured data in the CSV file, but what we are dealing is an images. We are dealing with an images. Now, some time back we have seen how do an image is represented. Image is represented as a matrix, and it will have the rows and it will have the columns, and along with that it will also have it will also be having the channels. So, if it is an grayscale, the number of channel is 1. If it is a binary, the channel is 1, and if it is an RGB, the channel is 3. Okay. So, for an neural network, what is an input? Input is an image. Now, in an image, we have image is represented as the collection of pixels. So, what is the dimension of an image? The dimension of an image is denoted as a number of such pixels in each of its row and in its column. So, for example, if you consider an image of size 28, 28 and 3, what is the meaning of this? The height of this is 28, the width of this is 28, and 3 indicates we are taking an colored image RGB. Therefore, the number of channels here are. So, internally how is that we are representing? We have 128 cross 28, this is a second 28 cross 28, and this is the third 28 cross 28. Now, what is each of these each of this image is represented by a pixel. So, here a pixel is a feature for an image. So, if you look into 28 to 28 into 3, the value is 2352. The value of this is 2352. So, which means we will have 2352 as an input for this neural network. Now, if 2352 number of neurons is passed as an input to a hidden layer, just imagine how many number of weights that we are going to have it. Every neuron is connected to every other neuron. So, in this particular place we have 2352. So, every neuron is connected to every other neuron. So, you can imagine what will be the complexity of a model. And if you look into this 28 cross 28, this is such a low resolution image. So, where you cannot be able to understand any feature which is present in the image. So, if you increase the dimension of an image, say for example, someone is working with an image of a dimension 200 cross 200, once again you are working with colored image, therefore, the number of channels here is 3. So, when you are working with this dimension, the size of this will be almost, the size of this image is 1,20,000. So, it is something which is very, very complex architecture. Therefore, we cannot go for images, we cannot use multi-layer perceptron. Little more let us get into the technical aspects why one cannot go for multi-layer perceptron when we are dealing with images. Now, see here is an example 2. Now, when you look into this 2, the 2 is represented in the form of a matrix. So, what is this? It is represented in the form of a matrix where you can see there is no information which is present in the corners. So, all this is 0. So, in the matrix, because black is represented as 0, so all these values are 0. And there is some information which is present here. So, therefore, you can see there are some values which are present here. So, image, this is an image for our human eye, but for a system it is represented as a matrix of pixel values. Okay. Now, what is the size of this? The size of this is 7 cross 7. So, since it is an grayscale, so the number of channel here is only 1. Therefore, the size of this image is 7 cross 7 into 1, which is only 7 cross 7, 49 number of neurons. So, when we convert this into an single vector, this 2-dimensional data, when you convert that into a single vector, this is what is a single vector representation of this matrix. Okay. Now, what is the problem with this? Now, since there are 49 such values, we have 49 number of in the architectural diagram, we have 49 neurons at an input layer. We have 49 number of neurons at an input. Now, every neuron is connected to every other neuron at a hidden layer. This neuron is connected to this neuron is connected to this neuron is connected, and so on and so forth. This neuron is connected. One neuron is connected to, if we have 49 neurons at a hidden layer, one neuron is connected to 49 neurons. The second neuron is connected to 49 neurons. Third neuron is connected to, third input is connected to 49. So, we have 49 features connected to 49 neurons at an hidden layer. So, how many number of such connections are there? We have 2401 number of connections, and on each of these connection we will have a weight. So, next, if you build the more complex architecture, I leave it to your imagination how difficult the model architecture will be. So, what exactly is the problem when we go with this kind of an architecture? Now, the minute we convert 2-dimensional into a single vector, we are going to destroy something called as a spatial relationship. This is important point. Now, what exactly is a spatial relationship? The spatial relationship here is how pixels are. Now, look into this matrix, how exactly the pixels are positioned here. In the first row, we have all zeros. In the second row, we have 0 followed by 87, 240, 210, 24, 0, 0. And in the third row, we have 0, 13, 0, and so on so forth. Now, whatever is the position of the pixel values in this matrix representation, the minute we convert that into a single vector, we are going to lose its position. So, this is what we are going to destroy the spatial relationship. So, what is the spatial? How exactly the pixels are positioned and how exactly the pixels are related to each other. Now, if we destroy, what exactly is going to happen here? Now, if you observe this very carefully, now here when you look into this image, we have something called as a curve here. And here we have a straight line, something called as a straight line, and again we have a curve. So, and here we have a curve. We have so the minute you convert a matrix into a single vector, what exactly is happening? Spatial relationship is lost. Along with that, the local dependencies are also lost. What do you mean by local dependencies? Now, which is the edges, corners, will not be no more edges or corners when it comes to a single vector. So, this is the problem. Now, what is the next problem? The next important problem is when it comes to an multi-layer perceptron, whatever the input that we pass to a neural network, each of the input is treated as an independent feature. Now, when you look into a data set, each of these features are treated independently for a neural network. Now, what is the input that we are passing here? If we are passing an image, when we are passing an image, we are passing a pixels. Each of the pixel is passed as an input to this neural network. Pixels cannot be treated as an independent feature, right? It cannot be treated. Why it cannot be treated? Because every pixel is related to its neighboring pixel. There will be some correlation between the pixels. So, this is one of the most important thing that we will be losing the spatial relationship when we deal when we pass an image as an input to a neural network. So, if this is not very clear, let us take a simple example. Look into this example. It is an example of 3 cross 3, maybe a small portion of an image. In a bigger image, we are just taking a small portion of 3 cross 3. Now, if you look into this, here the horizontal neighbors, if you take 1, 2 and 3 are the horizontal neighbors, 4, 5, 6 are the horizontal, 7, 8, 9 are the horizontal, they are the horizontal neighbors. Similar way, when we take vertical, these are the vertical neighbors, they are the vertical neighbors, they are the vertical neighbors. Now, what exactly is the problem? The minute we convert this into an the matrix should be converted into a single vector, only then you can pass it to a neural network, right? So, the minute you convert this into a single vector, just observe 2 and 5, observe 3 and 4. So, 2 and 5, here when we are in a matrix, there is a relationship between 2 and 5. What is the relationship between 2 and 5? They are the vertical neighbors. But when you look into a single vector, 2 is positioned and 5 is positioned in 2 different places. So, we have lost the information. Now, similar way, when you take 3 and 4, here 3 and 4 are the neighbors when you have converted that into a single vector. But when you look into an matrix, let me erase this so that it will be clear. When you look into 3 and 4, 3 and 4 are the neighbors in a single vector. But when you look into an matrix here, there is no relationship between 3 and 4. 3 is an horizontal neighbor and 4 is an horizontal neighbor for the next one. So, there is no direct relation here, but here they are the neighbors. So, this is one of the most important. We will be losing the spatial, we are going to destroy the spatial relationship. So, which we cannot afford when we are dealing with an images. Now, what is the next problem? Why can't we use multi-layer perceptron? The second problem here is when you look into parameter exploration. What is parameter exploration here? This is a simple input of 7 cross 7. If you imagine a little good resolution image, little higher dimension image, then the values will increase. So, you will have an exploration. So, with this the training will go slow, and then there is a very high chances of increasing the overfitting problem. There is a high risk of overfitting here. So, this is the reason why we cannot use artificial neural network, that is a multi-layer perceptron for an images. So, if that is the case, what is the solution for this? The solution is we are introducing a concept called as convolutional neural network. We will see that in a while. Before that, let us get into the last topic for this particular session called data augmentation. What exactly is a data augmentation? Why is that it is so important when we are dealing with an images? Now, look into this example. Here we have an X. Now, when you look from your eye, from the human eye, this is an X. Now, human is so intelligent that even when you show this image, human will still say it is an X. This is also a X for human. This is X. This, even though it is not very clearly written, so even this is also X for a human. So, for a human eye, it is for all these variants of X, this is an original image, this is original X, and all these are different variants of X. But human eye can able to say that all these are still X only. Similar way, let us take one more example. Let us consider this as 0. When you consider this as 0, all these are the different orientations or different variants of 0. Human eye can able to understand this. but this is not the case when it deals with an images. Why it is not the same? Let's look into the first two images so that we will be able to understand. Now, when you look here, these two are not the same for a system. Why these two are not the same? To that matter, all these images are not the same for the system. Here there is no information. Here there is no information, so it is fine. When it comes to this, here there is no information, but here there is some information. Similar way, here there is no information, but here there is some information. So, for us all these are the different variants of x, but for a system they are different, but this should not be the case, right? How do the system, how do the model handles, our CNN model handles this particular scenario? Therefore, we have a concept called as a data augmentation. What is a data augmentation? Data augmentation, it is a technique or a tool which is used to, this is an artificially you have increased. We are artificially increasing the size and then the diversity of the training data set. Okay, we are doing two things here. We are artificially increasing the size and then the diversity of a training set. How are we increasing it? How are we increasing all of these? By modifying the existing original data. So, we have a modified existing image. From the existing image, from this existing image, we are creating the different orientations of this. So, this is called a data augmentation, where we are artificially increasing the size and then the diversity of the training data set. And how are we doing it? We are modifying the copies of the existing image. Why is that we have to do this? This will help the model generalization. It will have a better generalization and thus reduces the overfitting. So, let us go in detail about this data augmentation. In the data augmentation, the very first step that we use is we rescale it. Now, if you remember in our multi-layer perceptron, we do something called as a normalization. If some feature value is very small, if some feature value is very large, in order to avoid the unintentional bias to a model, we are going to normalize so that all the values will fall into a particular range. So, the same thing when you look into this particular image, there is one pixel value which is very small, there is one pixel value which is very large. So, in order to avoid an unintentional bias here also, we are going to normalize it. How are we going to normalize it? Take each of the value and divide it with 255, because the maximum value pixel value will range between 0 to 255, which is when you normalize it, you want to bring down the values between 0 to 1. So, if you want to bring the values between 0 to 1, it has to be divided with 255, right. So, take the first value 205 and then divide it with 255, we get this value. Likewise, take the second number 119, divide it with the 255, we get this value, and so on so forth. So, this is the very first data augmentation or pre-processing step that we use, where we are going to normalize the values. How are we going to normalize it? Just bring down the values between 0. This is the value between 0 to 255, and these are the values between 0 to 1. And why is that, just for an better understanding, why is that we have not written it as 1 divided by 255, why is that we have written it as 1 dot 255? Why is that we have written this dot here? This is just for an Python, in Python version 2, when we write 1 divided by 255, it is called integer division, but from Python 3 onwards, it is an floating division. So, just to make sure explicitly it has to be a floating point division, we are writing it as 1 point divided by 255. This is just for an Python convenient sake. So, let us look into how are we going to increase the variance of it, how are we going to do this. So, we in Keras we have an important package called image data generator. We have an image data generator which is a part of Keras. And why is the on what we are applying? We are applying this on an image, and this is a part of a pre-processing step, and Keras is a part of TensorFlow. That is the reason we are writing it as from TensorFlow go into Keras into pre-processing. Under pre-processing we are applying onto images. So, import image data generator. Now, what is the image data generator? Image data generator is a tool which is used now to artificially increase the samples. How is that we are increasing the samples? What is the package used? It is an image data generator. Okay. To this image data generator, there are different parameters that we will be passing. What is the first parameter? The first parameter is whatever the image that we are going to pass to this, that image should be normalized. How are we normalizing? We have just seen an example. Each of the pixel value will be divided it with 255. And second important parameter that we are passing is shear range. Now, what exactly is shear range here? It is nothing but you are slanting the shape of an image. So, if you look into this is the original image, what exactly the meaning of this shear is? Shear is a slant. So, how is that you can slant? When you are dealing with the two-dimensional one, you can slant along with the x-axis, or you can even slant the image along with the y-axis. So, shear range is slanting of an image. Now, this is the original image. By creating a slanting, is it not we have created one version of an image? By slanting along with y-axis, is it not we have created one more version of an original image? Yeah. So, and if you look into, there is one floating number. What is that floating number? This is an hyperparameter. You can change this value. Now, whatever the example that we have taken here, it is 0.2. Now, what is the math that goes behind this shear range is this 0.2 will get multiplied with 180 divided by pi. So, you will have 0.2 multiplied with 180 divided by 3.142. So, we will get somewhere the value between 14 I mean you will get a value somewhere 11 point something. So, now if you look into thus when we write just only one number 0.2, actually the value will range. It is a range. When we say a range, you will have two values between these two. So, it is plus 0.2 to minus 0.2, that is the range here. So, you will be slanting from 11 degrees, positive 11 degrees to negative 11 point something. When you do this calculation, you will get 11 point something. So, since it is from plus 0.2 to minus 0.2, you will have radians, right. So, it is a degree. So, this is the degree with which we are going to slant the image. So, this is all about the shear range. Then, so this is one example for a shear range. If you look into, this is the original image, and we want to create an orientation or different variant of this image. So, how are we creating? The very first parameter is the shear range, and by applying a shear range, we can see that there is a slight slant of this original image. So, this is one of the variant that we have created by using this shear range. The second is zoom range. So, let me clear it so that you will have a clear understanding. Now, what we are discussing is a zoom range. Now, zoom range here, the value that we have fixed is 0.3. So, mathematically range, always a range will have two numbers. What are two values here? Mathematically it is 1 minus value is 0.3 and the second is 1 plus 0.3. So, the range here is between 0.7 to 1.3. So, this is the value. So, for now just understand independently each of these parameters, later we will be seeing with an example. So, when you take a shear zoom range you will have the value between 0.7 to 1.3. How did we get this 0.7 when we are passing 0.3? The math is 1 minus value comma 1 plus value. 1 minus 0.3, 1 plus 0.3 will be 0.7 to 1.3. Okay. How does this looks? Now, can you look into, you have this original image and these are different versions of different orientations of the original image. So, now what is an advantage of going for zoom is we can able to recognize the objects at a different scale. This helps the model to recognize the objects at a different scale. So, this is one more example. If you see, we have an original input here, and then all of these you can able to see them with a different scale, where there is a zoom in and a zoom out here. And next, this is all about a zoom. Then we have a horizontal flip and we have a vertical flip. What are the two values that we can give? Either you can make horizontal flip true, vertical flip as true, or you can make it as false. How does that particular example looks like? So, if you see, this is the original image. This is the original image for what we are now discussing is a horizontal flip and vertical flip. This is the original image. When you do an horizontal flip, the original image will be in this, and if you do a vertical flip, it is in this particular one. Now, is it not with one original image we can able to see a different orientations of an original image? So, is it not artificially we are increasing the size of your training data set? And how are we doing? We are doing a slight modification. Now, by slanting we have not lost the cat, it is still the cat only. If you look into by doing a zoom, we have not changed the animal remained the same, the input remained the same, but we are looking into this image from a different orientation. So, this is the different parameters. It is just not only these 5 different parameters, we have different parameters also, we have more different parameters. Let us look into it. Before we go into different set, the next parameter is width shift range. So, the next data augmentation parameter is width shift range that will be passing to an image data generator. What is this width shift range? Width in an image, this is the width, right? This is the width and this is the height and this is the width of an image. Now, what is this width shift range tells? We will be able to move this image, whatever the image, we can able to move this image right, or we can able to move this image left. So, we can move the image horizontally towards the left or towards the right. Now, how much you want to move towards the right, how much you want to move towards the left is the value that we are going to fix it. So, if you see here, the value that we have fixed is 0.2. Okay, and what is the mathematics that goes behind is, it is 0.2 W. What is this W? W is the width. In terms of number of pixels of an image. Suppose if you take the width size is 200, that is we have seen the dimension of an image is always represented as a number of pixels in the column, number of pixels in the row. So, width number of pixels here are 200. Now, if you take this example, 0.2 into 200, we get to 40 pixels, which means if you write 0.2, you have minus 0.2 to plus 0.2, which means you will be moving, minus is minus 40 pixels. The minute you write a minus, it will be moving towards the left. it is left, and then plus is plus 40 pixels, which is you are moving towards 40 pixels towards the right side. So that is what has been written here. Left is negative and right if it is a positive. Now, so how exactly it looks when you shift the image towards right side, 40 pixels if you are moving towards right. If you see, the dimension of an image has not changed, the dimension of an image has remained the same, but the image which is the object which is there inside is being shifted, the image is being shifted right. Now, when image is shifted right by 40 pixels, then because it is moved towards right, the leftmost will be empty. Right, when the leftmost is empty, then you have to fill those leftmost. How is that we are going to fill that blank spaces? The blank spaces are filled using an parameter called fill underscore mode. So, similar way, when you take towards the left side, this is shifting right and this is a shift left. Now, how much you are shifting? You are shifting 40 pixels towards the left side. When you are shifting 40 pixels towards the left, then right becomes empty. When right is empty, you have to fill those pixel values. How is that we fill those pixel values? We fill them using fill underscore mode. The function used is fill underscore mode. Okay. So, let us go in detail. I hope this is clear to you. So, width shift range is mainly used to shift the image horizontally either towards the left side or towards the right side. So, whether to move left or right, that depends on what is the value here. Whether if it is a negative value, you are shifting towards the left, if it is a positive value, you are shifting towards the right. How much to shift, that depends on what is the width of the image. So, you will multiply it with the pixel, you will multiply W with the value here, and whatever is the pixel values that we get, so many pixels will be moved towards the left or right. Now, let us get little more detailed into fill underscore mode. The possible values that we get for fill underscore mode is, you can write now what exactly is fill underscore mode. Now, when we shifted the image to the right, the leftmost portion of the image becomes empty. When you shift the image towards the left, then the rightmost portion of the image is empty. Now, how are we filling those left out portions? You can fill them using either nearest. So, if you are filling it, let us take this image in the pixel representation. This is just for you to understand. We have taken one image and this is the matrix image represented in a matrix form. Now, let us assume we are shifting this towards right by 1 position. If you shift it right by 1, can you imagine if you shift everything towards right by 1, we are going to lose this entire. Okay. Once we lose, then this portion becomes empty. If this portion is empty, this will be empty. If this is empty, how is that you are going to fill that? So, you will be filling it using a nearest. If you are using it a nearest, what do you mean by nearest? Whatever are the nearest pixel values, the same pixel values will be repeated in this empty. So, if you look into this example, so here all of these are the same. So, it is like something is being dragged. So, whatever is the latest, let me erase and then show you. So, whatever is these latest pixel values, these pixel values, it is the same pixel values which is repeated in all of these places. That is the reason you are seeing that the values, it is all the same here. So, this is called nearest. If you write fill underscore mode equal to nearest, then the nearest pixel values will be filled in that empty space. Second, we have a constant. What is a constant? Now, when you move towards right by 1, the leftmost is empty. So, in that leftmost empty, we are going to fill one constant value. That constant value is 0. Then you will see that in all of this place, you will be seeing a black patch. Okay. Next we have a wrap. What is a wrap? Now what has come out? When you shifted right by one position, what has come out, that is used to fill the empty space. So you see here, this is the data which had come out, and then we had an empty place here, we had an empty here. Therefore we are going to fill what has come out, you are going to fill in that particular. So this is a wrap, and the last one is reflect. What is a reflect? Reflect is an mirror one. Now let me erase to show you how exactly the reflect works. Now when we shift this right by one position, then we have lost we have lost this particular, and we have empty in this place. Okay. Now when you stand in that empty place and when you see, what is the mirror reflection we get? The mirror is in an empty position. When you stand and see, what you see is these pixels, right. So when you use the reflect, it is those mirror reflection is what is being filled. This is called width shift range. Similar way, width shift range is moving the image horizontally. Similar way, we have something called as height shift range. So in this place we have height shift range. What is height shift range? You are moving the image vertically upwards. You are moving the image either up or down. So, but the working mechanism, everything will remain the same. So when you see the width shift range, how is that it looks? You will see the image moving either towards the right, or you will see the image moving towards the left side. So can you see one single image, but you have a different orientations. So similar way, when you take an height shift range, what is the height? You are moving the image up or down. So but working mechanism will remain, the math, everything will remain same as the width shift range. So the value will be 0.5 h. And minus 0.5 h. In width we have seen 0.2 w minus and plus 0.2 w. W here is width, and for height shift range we will take h. Whatever is the h value, you will multiply with that, and so many pixel values will move in the up or in the down direction. Can you able to see how the images have moved in up and in down direction? And the last one we have is the rotation. What is rotation? When we write here 90 degrees. So the minute you write 90 degrees, it is minus 90 to plus 90 degrees. So you can have the orientation in all of these, for one image you can have 90 degrees, for one image you can have 87 degrees, for one you can have minus 45 degrees. So this is the example for rotation. And whenever we deal with width shift, right shift, we should compulsorily use one parameter called fill underscore mode. Here fill underscore mode, what we have defined is nearest. Now the most important step is whenever we go for data augmentation. Data augmentation is a technique that is applied always only on the training data set. It is not applied on a test data set. Therefore, you see this entire is being given to a train underscore data gen. But when it comes to an testing images, for test images we are only going for a rescale, but none of these data augmentation parameters have been passed here. So with this, what we are understanding, data augmentation is something that has to be done only on training data set, but not on a test data set. That is an important step that you need to understand. Okay. So let us get into the concept here. Let us take an example and then understand how we are creating a different orientation. Let us assume I have a training data set, and the size of this training data set, we have 112 images. Now when we have 112 images, we have seen that optimizers will take the data in batches. So we have a batch size also. What is the batch size that we have defined, the batch size that we have defined here is 16. So, when so from 112 images, when I am taking only 16 images at a time, then how many times I need to repeat so that I will complete 112 images? So, is it not 112 divided by 16? Which will be closer to value 7, which will be I think exactly 7, right? Yeah, or you may even get here in this example you got the value 7, but for some other example you may even get some value in terms of point, then use a seal and then convert it into a next integer, higher integer value. Okay, 7 times you need to repeat so that you will complete this 112 images. Good. Now, let us assume the very first out of this 7 I am taking the first batch per steps. So, this is the first 16 images I have taken it from the training data set. Okay. Now, the first image what you have taken from this training will undergo all these transformation. Let me erase this. The first image what we are taking from the training will undergo all this transformation. What is this transformation? Why it is going through this transformation only? Because that is the values that we have defined here. For shear range should be 0.2. The minute you write 0.2, it is from minus 0.2 to plus 0.2. So, if you see all of these values will all of the values here will range between minus 0.2 to plus 0.2. So, the first image will between minus to plus, randomly it has chosen this value. And zoom range defined here is 0.4. So, when it is 0.4, the value will be 1 minus 0.4 is 0.6 and 1.4. So, all of these values what you are seeing will be between 0.6 to 1.4 only. You will not see any other value. Then we have horizontal flip either true or false, vertical flip either true or false. Then width shift range, here since the width value what we have defined is 0.2, the value will be between minus 0.2 to plus 0.2, and similar way minus 0.5 to plus 0.5, and the rotation what we have fixed is 90 degrees. So, it will be from plus 90 degrees to you will have between minus 90 degrees. So, whatever the values for the first image, randomly it pick one of the value and that parameters are applied on this image. Then can you imagine what would be the orientation of that image? Then you will take a second image. That second image will go through this entire image data generator. So, there randomly it will pick again one more set of values, and what values we have picked? Let us assume the values are these. When you apply these values onto the second image, can you imagine how this image orientation would have been? Similar way, third image will go through these orientation, fourth image will undergo this values have been applied and it will take one shape. Similar way, all 16 images will go through this. So, is it not a different orientations of an image we have taken by doing this process? This is from this 7, this is the first one that we have done. Similar way, you will take the second set of 7 images from the training, and these now will not again undergo these values only. Now, it will go again a different set of values, but it will restrict within whatever you have defined here. So, with third set of 7 images will go through a different orientations, fourth set, fifth set, sixth set, seventh set. By end of this you are completing one epoch. What if you run this for 50 epochs? Can you imagine how many different orientations you are creating, variations we are creating? So, this is what we are artificially increasing the size of the training data set. And how are we doing? By modifying the existing data only. From the original data we are taking, and then we are applying all of these parameters. With this, let us see the continuation of the next topic, continuation of the previous topic. How do you store the data for a CNN model? Now, when you take multi-layer perceptron, you had data in a CSV file and you were passing that data to read underscore CSV or read underscore Excel if you are storing an data in Excel format. So you were passing into that particular function and the data was in the CSV file or in the Excel file. But here we are dealing with images. When we are dealing with the images, how is that you should store the data first and how you can pass that data to an model. So here if you are dealing with for example, you are working on COVID data and you have a training data and then the testing data. So create one folder called COVID and then inside that create a subfolders, and the first subfolder is a train, second subfolder is a test. And again if it is a binary classification, again under training you will have COVID and non-COVID. Similar way for a test you will have COVID and you will have non-COVID. Now, so how is that we have created a folder, under that we have subfolders, under each of these subfolders we have again a subfolder. What is these subfolders? Subfolders is where you are storing a class labels. Now, under training you have COVID and non-COVID. COVID is one class and non-COVID is one class. So, the with that class you will store the folder name. Since it is a binary classification, you just have only two here. If it is a multi-class classification, say for example benign, border case and malignancy, you will have three such subfolders under train and test. So, how is that during hands-on implementation, how is that we are storing, or how is that we will be passing this? There we had read underscore CSV or read underscore Excel, but here we will be using something called as a flow from a directory. Now, flow from directory has a certain parameters, and what are those parameters? The very first one should have a path name. And what is this path name? The path name, if you look into this flow from directory, the flow from directory expects a path, and where each subfolder, each of these subfolders are treated as class labels, and all the images which are stored under this COVID and all the images which are stored under non-COVID will be automatically labeled accordingly. And these images, the images which are stored in COVID will get the label 0, all the images which are stored in non-COVID will get the label 1, or vice versa, or it can depends on alphabetical order, and it is done by Keras automatically internally. This is a flow from directory. Now, if you look into this flow from directory, this is a part of training underscore data gen. What is a training underscore data gen? If you see in the previous one, training underscore data gen is this. Can you recall? This is a train underscore data gen. You have defined all the data augmentation, pre-processing, data augmentation parameters, and then you have assigned it to a variable train underscore data gen. So, when you see all the images which are there in a training set will go through this train underscore data gen. So, what exactly mean by this? Every image in the training will be going through all of these data augmentation parameters. That is what is written here. It handles the image pre-processing and the data augmentation. Flow from directory, we have seen that it expects as a subfolders and each. We have something called as target size. What is a target size? Now, when you collect the images, when you collect the data, maybe some image will be of one dimension, other image will be of a different dimension. So, what we are going to do? But a model expects all the images should be of same size. So, here we are defining what should be the target size, what should be the width, and what should be the height, what should be the x and y, height and width. Target size, it can be either 64 cross 64, or it can be 32, 32, 512 cross 512. What is the target size that you want to fix it? Then we have a batch size. What is a batch size? During the training, how many samples in batches you want to pass the data for a model to get trained? It can be 8, it can be 16, or it can be 32, or it can be one of the it can be a value here. And the last one, we have a class underscore mode. When do we write it binary? When do we write it as categorical? Here the example what we have considered is a binary classification. Because it is a binary classification where we are dealing with only two kinds of labels, that is COVID and non-COVID, then class underscore mode will be binary. Suppose one is working on multi-class classification problem. For example, somebody is working on cancer detection where you have benign, malignancy and border case. In that case, class underscore mode will become categorical. So, I hope this is clear to you. With this, we have come to an end of the first session in week 3, where you are going to learn CNN here. So far, if you quickly look into the summary, we have started with the fundamentals of image representation, where we have seen how many number of channels are there for each of. We have considered 3 different types of images. We have seen binary, grayscale, and then colored image, RGB. So, and the number of channels for grayscale and binary, the number of channel is 1, and for an RGB, the number of channels here is 3. And then we have immediately seen why not use a fully connected neural network for images. Ideally, the most important is it is losing the spatial relationship. And then we have finally we have seen what all different data augmentation techniques are there. You know, how is that we can able to perform this data augmentation using image data generator in Keras, and how do you load and store the images for implementation. This is done by using a flow from directory. So, with this we have seen you know, the basic fundamental. This will lay the strong foundation for understanding the CNN components, and that we will be doing it in the upcoming session. So, in the next session we will be going into the architecture of convolutional neural networks, where we will see what all the different key components, what all different layers are there in a CNN. The different layers includes convolutional layer, we have pooling layer, activation function, and we have fully connected. So, in the upcoming session we will look into the introduction to convolutional neural networks, and then we will understand the very first layer here called convolutional layer in detail. So, till then, thank you so much.